Okay, nice to meet everybody. Yeah, so I'm Steve Addy. I work at the James Hutton Institute here in Aberdeen, and I am, excuse the very jargony job title, I'm a hydromorphologist. In other words, I'm interested in looking at the physical form of rivers and how they change through erosion and deposition, and what the implications are for river restoration, but also how we manage flooding, in particular using natural flood management techniques. And to give a quick overview of today's presentation, firstly, I'm going to talk about the context of the uplands and some research that we've done on wood and leaky barriers. So I'll speak for about 20 minutes about that, and then I'll pass over to Mark. We might have some questions before that. Then I'll pass over to Mark, and then he'll sort of talk about a wider range of measures from the uplands to the lowlands.
Steve, you might want to switch it to percent of view. You're on your notes.
Um,
Just go to display settings at the top.
Display settings.
Just go up to your top bar. I can see it on your screen. Display settings. You're close to it now with your mouse.
Oh yeah, it's
Click on display settings and then say swap.
yeah, I can't see it because there's another kind of bar that's appeared. Stop video. Is it that? No. Show taskbar.
Next to show taskbar. There you go. The drop down menu there. Nearly to it. A little bit more to the right.
It's not appearing. That one, is it? No.
You're nearly there.
No, I can't get it, I'm afraid. Right, any bright suggestions?
Maybe stop sharing and then reshare on this different screen.
Okay. All right. Apologies, bear with me.
Oh, don't worry, take your time, Steve. This is our fault because we were joking how the technology was actually playing the game this afternoon.
Exactly, yeah. Jinxed it. Right. How does that look?
Perfect.
That's it.
That's us.
Perfect. You're
That
on.
better? Right. Okay. So yeah, I'm going to talk about wood and leaky barriers for managing water extremes, so flooding, but also droughts. Mostly I'll talk about flooding, but Mark will talk a bit more about tackling droughts with these kind of features. And yeah, I'd like to acknowledge a number of colleagues who've helped with this work who are listed at the bottom. Very much a team effort. So to give some context on upland catchments, they are very important areas for farming and culturally and for recreation, as we all know. And they are key areas also for the generation of floods because of the steep topography and often the wet and organic soils, which result in rapid runoff. And they're also key areas for the input and source of a lot of sediment that goes into our river systems, in particular coarse sediment. So that's sediment that ranges in size from sand through to gravel, through to pebbles, cobbles, and all the way up to boulders. And sediment is a very key part of river systems for its ability to create and maintain habitats, but it does also cause some issues further downstream. For example, leading to the clogging up of bridges and culverts, and it can also lead to loss of conveyance capacity in rivers, so their ability to take river flow, and this can locally exacerbate flooding. And upland catchments are very sensitive to climate change, but also increase coarse sediment delivery. So we need to try and tackle these aspects in upland areas so that we can hopefully mitigate the impacts of climate change. You're probably aware of wood and leaky barriers in streams. So here's an example at the top of a naturally occurring one. So they basically are usually generated where you have large pieces of wood, say a whole tree falling in and it's snagging, where there are constrictions in the shape of the river. And they can become very stable features and accumulate even more organic material and woody material and create leaky dams, as we see here. And traditionally in the past, they've been taken out due to concerns often about increased flood risk locally and also the impact it has on migrating fish. But there has been a bit of a kind of change in the way in thinking how we regard leaky barriers. So we're now actually trying to emulate these naturally occurring wooden accumulations in the form of engineered leaky barriers like we see here at the bottom. And these are generally aimed to reduce flood peaks, but they could help sustain base flows during droughts by wetting up floodplains and soils. And they also have a role to play in capturing and storing sediment. But there's a lot we don't know about how well they work, what the responses are to these features, and this research is needed really to inform the successful placement and design in future. So when we're trying to sort of summarize what leaky barriers potentially do, here's an example of a constructed one from the Scottish Borders. They have a range of effects. So obviously there's the damming effect that they cause. So this can lead to ponding of water upstream and storage of water, temporary storage of water. They also create hydraulic drag and roughness. So in other words, they create resistance to flow, which results in reduced stream velocities. And these aspects can also lead to improved connection to the floodplain. And on those floodplain areas, you can in turn have temporary water storage and conveyance of flow. And also you've got potentially the roughness effects of the floodplain coming into play as well. So where you've got vegetation, in this case, you've got bracken and rushes, for example, they're quite rough sources of roughness provided by vegetation. And then also they have the potential to accelerate flow if you've got a lower gap underneath the structure, as we have here. And this can lead to scour of the bed. And all of these effects could result in reduced and delayed flood peaks downstream. But that question still remains, but it's still very much an active area of research. But then when we're dealing with the potential geomorphic effects, so how these structures potentially alter erosion and deposition patterns and modify the shape of rivers and streams, potentially they could cause the deposition of sediment upstream and also channel scour, as I alluded to earlier, underneath the structures where you've got acceleration of water. They also have the potential to capture sediment on the floodplains, improve that process. And there's the potential also to trap debris, so other woody material and vegetation as well that comes down the stream and floods. And ultimately, all of these processes could lead to reduced coarse sediment delivery downstream. So I'm going to talk about two case studies in this talk. And firstly, I'll talk about the Elm Sike study site from the Scottish Borders. So this is on the flanks of the Cheviot Hills. And in this little catchment at the bottom of it, so the catchment area is less than half a kilometre squared. 16 of these leaky barrier structures were installed by Tweed Forum basically as a trial to see how well these structures could attenuate high flows and capture sediment. And in this catchment, as we can see going by the photos, there are some sediment issues. So on account of the quite mobile and soft geology, and also because of the land use potentially and a history of quite intense flood events, you get some quite significant erosion. So in this top middle photo, you can see an example of an erosion scar and a head cut where the channel has incised by about a meter or so. And this sediment then in turn is moved as a bed load during flood events down towards the bottom end of the catchment and deposited in this alluvial fan. And you've got, in this example, you can see about a meter of coarse sediment here that's been caught on the fence line at the bottom of the elm site. And the other thing that we undertook, to step back, we undertook some monitoring of how well these structures alter the geomorphology, how much sediment they capture, but also through using hydraulic modeling, we've been able to make an assessment of how the structures alter the patterns of water movement, so how they alter the velocity in the stream. So here there are the results of some modeling that we did. So in the top image, you can see the reach without the structures in place. And then in the bottom image, you can see with the structures, the effect on water flow is generally quite limited. So the areas of yellows and reds are the higher velocities, the areas of blue are the lower velocities. And we can see there isn't that much of a change between the two images. But that said, when we looked at the reach scale change, there was a slight reduction in the velocities as a result of the leaky barriers, but also because of the sediment deposition that occurred within the reach, which had the effect of connecting up the areas of floodplain pockets and shallowing the flow. And also this increased the area of flooded water within the reach as well. But again, it was quite a small change. And then when we looked at the geomorphic changes, in particular how the structures captured sediment, how much of that sediment they caught and kept, you can see in this map here, we've got an elevation change map. The blue cells show where you've had deposition. The yellows and the reds show where you've had erosion. And the response to the leaky barriers was quite variable. So in some cases, we've had scour underneath the structures. In other cases, you've had significant deposition of sediment. And this sediment, once it was caught in some early flood events, it was retained behind these structures for the duration of the monitoring, so over a 3-year monitoring period. But the biggest catcher of sediment in the reach was actually this sheep screen, which caught about 2 cubic meters of sediment. So maybe sheep screens have a role to play in reducing sediment yields in catchments. So to summarize the key findings from the Elm site case study, they had no significant effect on peak flow travel speed. In other words, they didn't delay the onset of a flood downstream. This was based on our observations of the timing of flow peaks through the reach, which I didn't go into in detail. And the modeling did show that the structures only slightly increased the flood area and only slightly reduced the water velocities. But overall, the 16 structures did capture nearly 4 cubic meters of sediment over 3 years. So for a small burn and catchment, not an insignificant amount of sediment was caught and retained by the structures. And we also found that the sediment deposition was most likely where the lower gaps so the gaps between the structures to allow the movement of water during dry periods. It was at its greatest where it was less than 40 centimeters. And where deposition occurred behind the structures, it was having a greater effect on the water velocities. So by shallowing the flow and spreading it out to the floodplain, you could actually reduce the velocities more and take more of the energy out of the stream during floods. And this also increased the flooded area more significantly than the structures too. But overall, the hydrological effectiveness of the structures was limited, and this was due to the very steep nature of the channel and the lack of floodplain pockets, which could be reconnected to increase the storage. And another factor was because the structures were closely spaced, which meant that their backwaters, their ponding, was being interfered by the next structure upstream. And lastly, the structures were quite small in size, which resulted in limited floodwater storage. If you want to find out more about this case study, that there is a paper which is given in the reference here, which is really available. So moving on from that case study in the Scottish borders to a different case study in Aberdeenshire. So this is our Cairn Burn monitoring site, and this is a before-after control and impact study that we have here, looking at the effects of a different design of leaky barriers. The catchment size is slightly bigger than the Elm Syke in the Scottish borders, but yeah, there are some similarities in that, again, it's a steep, high-energy catchment where you've got rapid runoff. And really, with this monitoring experiment, we're trying to build on the lessons of the Elm Syke case study, but also other leaky barrier studies from the UK. So at this site, we had 7 leaky barrier structures installed, and these give a total storage of 73 cubic meters. So that's storage of water, theoretically. And unlike the ones on the Elm Syke, they weren't put in a regular series, so with regular intervals between the structures. Rather, we put them in points of the stream where the water was shallow and where the stream was already connecting to the floodplain. And we also extended them out onto the pockets of floodplain and put them within floodplain channels, old channels, and hollows. So basically to try and kind of intercept and store as much water in the reach as possible. And the 7 structures were built in March 2023, and the monitoring has been ongoing since then. And also in tandem with the construction of the leaky barriers was the planting of the riparian area with trees. So a mixture of species ranging from alder, which do particularly well in these wet glade and organic soils and alluvial soils in the valley bottom. And also on the sort of upper slopes, we're putting in pine and birch, even some oak and some juniper as well. And the purpose of that tree planting is to basically create a roughness source within the floodplain and the riparian area, which we hope in the long term will further reduce velocities during flood events, and also it'll create a supply of wood in the future, potentially to bolster the leaky barriers. So when the debris from these trees or the trees topple in, for example, we'd like to see them captured on the structures we put in to maintain them. So here's a view of our structures here. So 7 in total, and quite different to the Elm Syke structures, which were only up to 4 or 5 meters or so in length. These ones are up to nearly 20 meters in length and extend out into the floodplain and into the hollows and channels where you often have overbank flooding. And so far, it's been very wet baptism for the leaky barriers, with the largest event occurring during the monitoring record being Storm Babette during October 2023. But we've also had drought conditions like the recent summer. So a lot of good data we've collected since the monitoring started. And this will help us to understand the range of responses to the leaky barriers for different hydrological conditions. We have at the site a time-lapse camera, and this is just to give an example of what happens during a high flow. And you can see the ponding and wetting up of the floodplain areas here. And this was something that we would plan to occur. And it seems to be working quite well for these two barriers. But for this barrier here, I don't know if you can see where I'm pointing. It's quite difficult to see. You can see that it's not intercepting any water. So the structures are having a quite variable effect on the movement of water, with some being more successful than others at spreading out and storing water during high flow events. And as we were on the Elm site, we've been monitoring how the channel and the floodplain change through erosion deposition. And in this one example, leaky barrier 3, it caught over a cubic meter of coarse sediment. And this had the effect of diverting the water down this channel here to leaky barrier 1, where it's ponded temporarily. So basically enhancing the process of overbank flooding into this natural flow path. But it's also had the effect of scouring this flow path here. So again, just illustrating range of effects that these structures can have, both on the dynamics of water flow, but also on the geomorphology. In contrast, further upstream, so LB4, for example, you can see that there's been scour underneath the structure. And then the remaining structures, there's also been quite a lot of scour too. And another thing we've been monitoring here is how the structures affect the water table level, and also the level of water when it's above the surface of the floodplain, so during flood events. And we're quite confident, although this graph doesn't show it so well, that the structures, certainly one or two of them, appear to be having the effect of increasing the water table level. So the water table appears to be higher than it was prior to the leaky barriers going in. And this indicates that the ponding of water is helping to infiltrate into the soil, and locally that could be quite positive in terms of retaining water and sustaining base flows downstream during droughts. So it's still work in progress with regards to the Cairn Burn monitoring. There are no indications yet that they are slowing or reducing flood peaks, but locally they are elevating water tables. And this is potentially positive for sustaining low flows during droughts. It's very much an evolving experiment, this. So we intend to undertake 2 new phases for this experiment. So firstly, we're going to add in new floodplain structures and 2 in-channel structures. And we're also going to plant willows as well in lines to create living barriers and monitor how well they work. And the monitoring of these developments will continue for the next few years, I should think. And if you want to find out more about this case study, there's a link here to a PDF which gives you some more information. I forgot to mention that this site is based at our Glen Saugh farm on the Cairn Mount. So this is our climate positive farming initiative farm where we have a number of experiments ongoing. And to give some overall conclusions on leaky barriers, are generally low cost. So the structures that were installed on the Cairn Burn, we employed a contractor to install them, and it came to a figure of £4,000 to install them. But I think it's possible to do them cheaper if you do it yourself, because they're quite low tech to install, and particularly if you've got your own timber to hand nearby. So at Glen Saugh, at the Cairn Burn site, we used wind-blown timber that come from larch that had fallen over in Storm Arwen in November 2021. But it's important to consider that the structures may need maintenance going forward. All of the structures on the Cairn Burn, the Elm site, have stayed in place, which is definitely a good result, because it just goes to show that in such high energy streams you can engineer these structures. But the longevity of the timbers is potentially an issue, which isn't so well researched. On the Cairn Burn, we're using larch, which tends to be quite long-lasting. And there is the potential for leaky barriers to mitigate floods in steep confined streams. This is based on evidence from the literature, although the evidence from the case studies I presented don't really support that. But we're quite confident that if you put leaky barriers in areas where the channel gradient is low, say less than 2 to 3%, and where you have floodplains, they can be small floodplain pockets, only 5 to 10 meters wide. If there's the potential for you to connect up those floodplains, then you've got much more in the way of added benefit to installing your leaky barriers in, by creating greater water storage, and because of the greater roughness effects, which will in turn reduce the energy and reduce the velocities of water flow during flood events. But also, yeah, there is a question of scale. So not surprisingly, you need quite large volumes. There seems to be a consensus forming that you need, say, up to 1,000 cubic meters of storage per kilometer squared of catchment to deal with, 1 year floods, to sort of attenuate them in a meaningful basis. So if we apply that rule of thumb, which you need to do with caution because every catchment is unique and different, every situation is different, that is equivalent to about 95 of the structures that were placed on the Cairn Burn. But also it's important to think about the roughness of the adjacent floodplain. So if there's the potential for this to be enhanced using tree planting, then that could potentially slow off runoff further and provide other benefits as well. And finally, leaky barriers have an important role potentially in storing coarse sediment in steep streams, but the long-term sediment trapping effectiveness and the design of the optimization of the design of structures to enable that is very much still work in progress. And there may also be maintenance considerations on top of that. So that's the end of my talk.
Brilliant. Thanks very much, Steve. And thanks, Mark, for sort of answering those questions in the chat. If anyone wasn't aware of the questions coming through, just click through the chat. and have a quick look at some of the answers that Mark's put up. Grand. Seamless transition, Mark. That's what we like to see.
Yeah, that's what we hope. So I'm just going to continue on because that's part one of the presentation. So hello everyone, I'm Mark Wilkinson. So I'm going to be talking about the wider benefits here and building on from the measures Steve talked about there. First, leaky barriers, and then looking at from the uplands down to the lowlands. The context behind this is how do we enhance the benefits of MBS and improve implementation in agricultural, both upland and lowland landscapes? So Steve has talked a lot about wooden leaky barriers there and the flood management benefits. But what I'm going to do here is now reflect on the low flow end of the scale. How can these measures be used to mitigate the impacts of droughts? But before I go into that example case study, I just want to say that floods and droughts are two sides of the same coin. Now, what do I mean by that? Well, at Glen Saugh, one of the biggest events we've recorded there was Storm Babette back in 2023. And in that storm, we had 200 millimeters falling in a 3-day period. So that's nearly 20% of the yearly average rainfall falling in 3 days. Now, what we're seeing with climate change or changing climate is a greater number of extreme events, so more floods, more droughts. One trend that we're not seeing is an increase in, say, yearly average rainfall totals. So what we're seeing here is a good dump of our rainfall coming down in 3 days and running straight out to sea. It's not really getting the chance to recharge. And then we tend to be seeing sort of longer periods of dry spells as well. So this isn't really helping the catchment storage situation, and we need to look at ways to try and hold that water for longer in catchments, either in soil, ponds, wetlands, to infiltrate, to improve low flows. So the case study I'm presenting now, part two of this talk, is staying in the headwaters, but I'm going to be looking in the uplands and look at how leaky barriers can be used to mitigate low flows. Where we're doing that is at Glenlivet Distillery. So the partners here are ourselves, University of Aberdeen, and the Glenlivet Distillery, which is owned by Chevis Brothers. They started off as an ERC project, but the distillery are keen to keep this work going at the PhD at the moment. So at Glenlivet, they're worried about future water resources. The future, they need water for distilling. They use a lot of water for distilling. It can be up to 1 million litres of water per day, and that's mainly for the cooling process. So they need to optimize that cooling. And summertime, they need that water to be cool and plenty of it. So this is a threat for the future that they don't have enough water for that. So they're looking for resilience through nature-based solutions. So we've looked a lot about MBS in the flooding context, how we can reduce and delay that flood peak. But what we actually want to do MBS in the low flow context is to make sure that that base flow, the water available in low flows, is higher than it is without MBS. So the way we do this is look to capture rainfall during the event, allow it to infiltrate into slow pathways through deeper or shallow connections, and allow it to re-infiltrate back to streams. And that also is good for the distillers because it comes at cooler temperature, because if the water is warmer, then they need more of it to cool the process. So we've implemented a range of trial leaky barriers. There's about 35 to 40 of these, a mix of wooden leaky barriers, earth barriers and stone barriers. They're quite small, but we've been monitoring these in detail to look at the water levels and how they're filling and draining. So we have lots of data from different types of intervention here. And we have lots of data as well from the wider catchment here. This is a 0.5 square kilometre catchment in Speyside. Jessica Fennell, a PhD student, characterised this. We used stable water isotopes and lots of different methods to characterise this. We've got a lot of knowledge, a lot of empirical knowledge, which is really important. But what we've been able to do with that knowledge is to inform a modelling tool. Now, I'll not go into the details of this, but we've implemented a sort of catchment-based model to look at sort of the surface flow dynamics and the recharge of this. And that's enabled us to look at different scenarios of MBS and how they're performing. So what we're looking here is the importance of design, how big, how many, and where are these leaky barriers. So you'll see scenario C is the current. We've got these leaky barriers on ephemeral flow pathways in this part of the catchment. But in A and B, we want to look at the location. How do they perform in different soil types? And in scenario D, we want to look at the scale, both volumes and spread of different interventions. So in summary, very briefly, the results look like this. The current setup of nature-based solutions, leaky barriers in this catchment, give us around about a 1% change in base flow. Now, there's a caveat here, there are uncertainties behind the model, but it shows there's a slight improvement. Now, that is very small, but the measures are very small. They're a set of small scale trial interventions. So these scenarios, therefore, allow us to understand how they would look under different placement scenarios or design scenarios. And these are the outcomes. And to break this down, firstly, if you look at MBS scenarios on different soil types, if you put these leaky barriers on more freely draining soils, you get a better impact than on poorly draining soils. And that just shows that the water on poorly draining soils is more difficult to infiltrate. So it's best to have it on freely draining soils compared to the poorly draining soils in this catchment. Next, the spread is important. So putting these over a wider area, so the same volume over a wide area has a greater impact than a smaller area. And that's just due to the fact that you're spreading the storage across the catchment area. And that's important when you look at volume, because actually the impact of volume starts to taper out. And that's just because once a pond gets wet and the soil gets wet, it has no further impact. So the key thing is here, soil type and a good spread of measures. Now, I should say that the results for flooding were similar to what you're seeing for drought here as well. So it shows that these measures have impact for both flood and drought. Now, we've done some work on cost benefit. Now, I don't have time to go into that today. We have a paper on this, but basically the distillery, the cost benefit of these types of measures is large. It's really large. And that's just because the measures are so cheap to install. We're talking about maybe a few £100 for each measure. I think about maybe 10K for the whole lot of them. But one day's missed production, lost production for a distiller. So imagine that just reduces one day's lost production is a very big figure. So that's why the cost benefit is good. So we're looking at future work for the distillery there. Jennifer, a new PhD student, is looking at sort of conceptual models for surface groundwater connections and looking at different distilleries and land types as well. And we hope this will provide guidance to the wider industry and other stakeholders such as farmers. So that's the sort of look at low flows here. And now I want to go down the catchment and then look at sort of the agriculturally productive lowlands and looking at how we can enhance the benefit of these measures or new measures in the lowland catchment. So I would just want to bring in the final 10 minutes a range of different measures just so the focus isn't just on in stream here. And the area I'll be looking at is sort of edge of field and riparian buffer. And firstly, before doing that, I just want to sort of the focus on this is both water quantity and quality, including soil erosion. And one way to conceptualize this risk of runoff in the lowlands is, and uplands too, is using what we call the floods and agricultural risk matrix. So the risk of flooding is much higher if you have poor or bad soil quality, so compacted, then your risk of flooding is higher. And if your flow connectivity, your flow paths are really rapid and take the water straight down to the stream, then you have a higher risk of flooding. So this really helps us to understand that the important things to look at here in the catchment is both soil management, very important, but also the flow connectivity pathways. And that's important when we're looking at catchment management in a real life situation, because if we have increasing hydrological extremes, then we're going to have more fast erosive flow pathways. And then that leads to our issues such as soil loss, floods, droughts, water quality issues. That's highlighted in these bottom images. This is our research farm down in Balrudry. And actually, a lot of the example I'll show you now is from moving from Glen Saugh, the uplands, which Steve presented, down to our lowland farm near Dundee, Balrudry farm. This is the Invergary catchment. Our farm manager, Ewan, took this picture. That's a 3-meter deep erosion channel. Again, storm Babette, so the same storm from Glen Saugh. And a few weeks, the few months prior, we also had some convective events, and that's kind of what was doing to the potato farming of the area as well. So you can see, is there a link between floodwaters in our sort of villages and towns filled with sediment? But yes, indeed, this water and soil is heading downstream, and those communities don't want that water, nor do they want the soil, nor do the farmers want to lose the soil. So we need to look at better ways to manage this. So a key philosophy we have is getting that right measure in the right place and delivering the multiple benefits. And I'm going to be ending on this thought of right measure, right place. So if we take that sort of edge of field margin and riparian zone, what we like to look at here is the 3D buffer concept. And if we say our sort of default standard is a standard 6-meter grass buffer, well, we kind of know that that isn't very effective at all for managing water quantity or quality issues. Water will still run off over that into sort of streams and ditches. So the way you improve a grass buffer is with multiple measures to maximize the benefits. And that can be a mix of either tree planting, riparian planting has been certainly evidenced to be better at improving quantity and quality issues of our channels, and also provide other benefits such as shading. You could look at things like design of vegetation, putting in sort of wildflower mixes, which will help our sort of arable cropping systems. And we've looked at things like magic margins here as well, adding structures to these little micro topography features. You can put an edge of field bund in here, and I'll come on to this one next as an example. So just store the water temporarily, allowing it to drain. And for more, where you have greater issues, you can look at these engineered buffer zones, these sort of bioecological zones, which improve water quality and quality. So it's all about targeting for the required environmental issue of concern. So if I look at raised field margins, what these measures are basically temporary storage areas, and that's a keyword, temporary, enhancing sediment capture. They also add new additional storage to catchments, which is brilliant for flood risk management. The more storage we can put into a catchment temporarily, the better we can manage flood peaks. And I'll come into that later slide. The land can still be managed, the footprint can still be managed, and they can have volumes up to generally 10,000 cubic meters, and that's based on reservoirs contents to try and keep them low, low storage. But guidance on construction is essential, and there's many sort of guidance documents out there, which I'll come on to, also flagged up on my references towards the end. But it just goes to show you can see from one example here, just a moderate event, that feature there captured over a ton of sediment. And then the work in Belford catchment, which we've worked on a lot. So one of the early examples of NFM, work from Alex's PhD here, showed the impact of, again, monitoring these. You can see an impact on the flood peak. If you were able to put 30 of these in a sequence, you can get 35% reduction. Although that is a small catchment, 6 square kilometre, which highlights that NFM summary that they work well for small catchments and small to medium events. Larger scale becomes challenging. But what we can get from this is communication with simple metrics. And again, a paper here produced by Martin Robert, PhD student, just graduated a year or so ago. He plotted the relationship between total temporary storage area volume, TSA, but this is per meters cubed per kilometre squared. So we standardized this and looked at peak flow reduction. And he used about 7 UK case studies. And what you can kind of see here is the more storage, temporary storage, new storage you put into a catchment, the greater the flood peak, the peak flow reduction. So you can see here about 2,000 cubic meters of storage per kilometre squared gets you about 10%. But what you can see here is many of the studies are modelled, and we need more empirical evidence to inform this. There's only a couple of big, truly empirical based studies on this plot here. Moving on to the quality issues, engineered buffers are great for this. This is an example we have in Balrudry, whereby we've broken. So what an engineered buffer is doing is actually dealing with the problem we many times we forget about, and that's subsurface field drains, the tile drains running through land. And what we've done here is sort of broken these subsurface drains into a mini wetland within the 10-meter zone, the buffer zone here. So you can see here the field drains cut back, small wetland, and we allow the water to filter through a bioactive root zone here. The plot on the right shows its impact on nitrate, a paper here my colleague Mark Stowe worked on. And you can see here that actually the nitrate levels of the drain, the water coming from the field, are much higher than those leaving in the stream. So you see a reduction in nitrate in this system here. But the key thing is you need more maintenance here in terms of cutting back this willow, but it could be an energy crop that the farm could use. So we've captured all of this material into resource. This is on fas.scot, 3D buffers, magic margins. We're part of this report here for the Environment Agency of 3D buffers. And there's also two other projects. Our RESAS project's a key one here, MMBS, but we've also done some work in Ireland on this. But one thing maybe to look at is here's our measure database, where we've looked at these edge of field measures and created a 16 measure database. I've only touched 3 of them today, but there's plenty more examples here that can be looked at in detail. And this evidence base we are intending to grow. These are just some of the initial results from the Smart Buffers project down here, web link. As for placement, well, where do you put them? Again, we've looked at this and we would say that our fixed linear width 2 meter compliant grass buffer is our baseline. But we need to look at putting more structure into our buffers. So if you had more diffuse pathways coming down a hill slope, like here, these blue lines are overland flow pathways mapped on using topographic data. And you can see you could put maybe a long linear woodland in here. Or you could put in designer vegetations down the flow pathways. So this is our Centre for Sustainable Cropping, and we have some of these as well. And these act as sort of beetle banks and allow ecological zones here. But a key one here is targeting these convergent flow pathways. So you can see where the water from many fields coming to one point, and that's where you can use raised field margins such as bunds. And then where you have more convergent field drains coming together, then you can look at things like engineered buffers, and that's exactly where this one's located here on our farm. So to conclude, design, location, and scale matter for effectiveness. Getting that right measure in the right place is key. But one thing to take home from this is it's not a one-size-fits-all approach. It's a range of different measures are needed and a treat and train approach, and looking at the right measures through a sort of a farm walkover and targeting them in the right place. So key thing to end on here is right measure, right place. And finally, just acknowledge the 2 projects I'm presenting here. The first part was Glenlivet and the people I've mentioned there, University of Aberdeen, Chivas Brothers, and the wider contributing officers listed here, the larger team. And then the top of the acknowledgements to our RESAS team as well, who helped to provide information for these slides. And that was funded by the Scottish Government there. And I'll stop sharing now. And that concludes the talk from myself and Steve.
Brilliant. Thanks very much, Stephen and Mark. That was really interesting, particularly I think for a lot of people in the call today who I'm noticing a couple of names are kind of based north of England as well as in Scotland. So that's all great stuff, really informative. If anyone has any questions they'd like to ask right now, I'm just going to launch the poll for this session before you all run off and jump in your diggers and get your chainsaws and start building leaky weirs. It'd be great to just capture some of your thoughts from that presentation, just because it helps us feedback to the guys presenting today, and also for the kind of wider program we're delivering. I'm just going to double check. Sorry, I've lost the chat box. I can't see if anyone's. You can't see if there's anything in the chat, can you, Rob? Seeing as you have access to the Zoom account.
Can't see anything. To be fair,
I've lost the window.
Steve and Mark have sort of picked it up as they've gone along. I'm just scrolling back up in case there's anything up near the top.
Oh, there is a missed question there.
There?
Steve, why do you think the sheep watergate was so effective? We've noticed this on our burn. Sorry, I missed that one. Oh, you've answered it. You answered it. Sorry, you didn't press reply to it. That's my fault.
Yeah. I didn't use the reply button.
No, that's fine. I think we've covered everything.
Grand. I suppose one of the questions I kind of have, which might appeal to some other people as well, this kind of method of holding more water in kind of strategic points on steeper ground, does that kind of persist into summer to the point that you could potentially graze areas that don't have water infrastructure using that water as a source for the animals to access? Or do you not see the water persisting in periods of drought? I suppose that depends on the ground itself, but
It does depend on the ground, and I guess you have to have a bit of caution here because do you mean for sort of watering points for livestock or yeah, I think the philosophy I would like to do is hold the water and get it infiltrating into the ground so it comes out a bit later. If you hold it in a fixed point on the surface, there's a few negative things that could happen there, such as poaching livestock going in because it will be boggier. So we don't want to be doing that. Also, there's a risk of losing water through evapotranspiration once it warms up. So generally open lagoons will lose water. So again, getting into the ground, there's a less risk of losing it through evapotranspiration because that is valuable water. So that's two things off the top of my head. You would need to think strategically. There could be ways to do it. Again, you could engineer a point to do that, but generally the concept here is improving our low flows through infiltration, and that's a key part of that, especially for Martin's work, is improving soil structure, even in the measure footprint itself. So it's not just about putting the measure out there. You've got to manage the footprint as well of the water you're infiltrating, because you can get things like sumping going on once there's been a flood. So generally, good maintenance of that footprint is key.
what do you mean by sumping?
So if water ponds for too long, I guess many people know this, ponds for too long, it can affect the soil structure. It can compress it and reduce the infiltration rates in there. So it can effectively compress under the strain of the water. To put it in simple terms, it's a bit more complex than that, but hopefully I've covered that in simple terms.
Yeah. And yeah, a couple of photos there, kind of 3D buffering put in place on more low arable ground. What is the kind of how mechanically involved is that? It looks like there's a fair amount of work to do there with diggers and kinds of things.
So I would be thinking to do things like raised buffers as part of an NFM scheme because that's adding a lot of temporary storage to catchments or maybe agro-environment schemes which support that. Which I think there are a few in England. There are sort of schemes that will pay for bunds, like making space for water. But it doesn't have to be that complicated. Things like our magic margin approach. Now, I didn't go into that in detail, but basically that is just creating lots of little storage ponds. And what we use there is potato furrows and a tide ridger, which creates the mini dams. You'd usually do that down the slope to create pockets, but you do that perpendicular. When the water hits that, it runs over into these mini pockets and infiltrates. But that also has a benefit of being able to plant that up with vegetation that you may choose, whether it is to increase pollinators, for example. But if you get the right vegetation, you improve the root zone and therefore improve the infiltration. Therefore, that point I was making about storing water becomes better because the vegetation is managing the soil, the roots.
Yeah.
There's a lot more information on that on our Magic Margin webpage, which I'll share in the chat in a second.
Yeah. Perfect. No, thanks for that. There's just one question there from Mark. Do you want to come in and ask?
Oh, hello. My name's Nicola. Sorry, I just jumped on my husband's computer. Yeah, just wanted to mention that we've put in some leaky dams and seen the benefits of them, both from doing it by hand, and then we've seen the sediment collecting in the leaky dam, and then sort of done it in a sequence, so done one at a time, so that they sort of collect the sediment and they build up and the leaky dam becomes established, if you like, and then moving upstream onto the next one. And I think that sort of makes sure that they're sort of maintained. So, rather than doing a load of dams at one time, then you can just sort of do them in sequence. Do you get what I mean?
Well, managing the sediment, yeah.
Yeah, managing the sediment and also establishing them, so they become strong and integrated, and the sediment is supporting the dam,
Okay.
and then move upstream onto the next one. So we've been working at them, by doing it by hand in a sort of more low-key way rather than putting them all in one place. So yeah, it just seems to work really well. Just thought I'd share that.
Okay, good. That's interesting.
Oh, great.
I've just spotted that comment from Ian in the chat, which I want to acknowledge because maybe I didn't stress that enough in the slide. Absolutely, we should be storing as much water in the soil as we can store on the ground. But I guess that's the point of the agricultural risk matrix. So it's about, to reduce flood risk, you need to manage the soil, definite. But we have to acknowledge when we have these big events, we will get runoff, and we even saw that example from Ballarudry there. That's generally good soil management down there. So we need to also manage the pathways. So totally agree, should store as much water in the soil, but we also equally have to manage our pathways, which are erosive, as we get these bigger, wetter, intense events kicking in. So hopefully that, I do agree with that point, Ian. And I guess, yeah, the focus here was on the pathway to follow on from Steve's talk there, but hopefully the risk matrix explained that a bit more.
No, brilliant. No, that's great. Thanks again, Stephen and Mark,